Thanks everybody. Thanks for turning up on day 2, but I suppose thanks also for not drinking all the scotch, because I see everybody bright-eyed and bushy-tailed, so thanks for that. As mentioned, Scott Treadwell, so I'm the president of SixRing. We're based in Calgary. I'm going to run through a few slides about our technology, but what I really want to focus on are, as you can see here, the pathways to commercialization, our two most promising near-term commercial outlets for our technology, and hopefully that kind of stitches the whole thing together. So in a nutshell, what do we do? So we've developed a low-cost, highly efficient, and effective chemical conversion of biomass to high-value products. And I want to be clear, I don't just talk about fuels, it's products broadly. And some of the big advantages we have, first and foremost, feedstock flexibility, pretty much infinite, and product optionality. And you can see there that product optionality replaces subsidies. So our technology, with the right planning, can self-subsidize the production of feedstocks for fuels that are cost competitive with the fossil equivalent. And to me, that's the leap forward our industry needs to make. If we can't be cost competitive, you know, with all due respect to the people down the street, they're going to run out of our money to spend one day. So our process is also very low complexity. The chemistry comes from commodity global chemicals, and we use simple stainless steel atmospheric tanks, happens at ambient temperature and pressure. That means everything is carbon advantaged, and we're not breaking things down with a thermal process. And this is based on 12 years of experience in R&D with this family of chemistry that first was developed for the oil and gas industry. We sold that business about 2 years ago and have spent about 5 years, almost 6 now, developing this application specific to delignifying biomass. So state of the world today, a lot of the existing technologies when we talk about biomass focused on food-based biomass. There's treatments, many of them are commercial today. As you can see on the bottom there, these always kick off a food versus fuel discussion. I won't call it a debate, it's not necessarily fully informed on both sides, but the headline doesn't really read well if that's the choice you're asking people to make or you're being accused of asking people to make. A lot of these processes are chasing fuels, so they're commodity products and they don't have a lot of product optionality. They're really good at making those products, but at the end of the day you're chasing, in a lot of cases, fossil fuel markets that have a 150-year head start in making the stuff and about a 100-year head start in getting us all addicted to using that stuff through cars and planes and trains and boats. So going up against that is truly David versus Goliath. It's not that it's not a battle worth fighting, because it absolutely is. But what it means is at the end of the day, what we see today is that subsidies typically are required to make things equivalent. We just had a great presentation on that on SAF. And to me, part of it is, understanding those incentives and credits, but it's also incumbent on all of us to develop those technologies that can be cost competitive. When we move to the other side of the slide and we talk about non-food biomass, there's a lot of technical challenges here, mostly around lignin, which I'll get into on the next slide. How have we overcome that? Typically, high temperature, high pressure, that means high carbon intensity. It also, in a lot of cases, means you limit your feedstocks. And on the right-hand side, what you see is that high energy process tends to give you a bit of a bell curve of products, carbon, hydrogen, oxygen, whether that's solid, liquid, or gaseous. It means that you typically irretrievably alter the chemical nature of the biomass. These products can be hard to process. I think we've seen some great innovations yesterday in biochar and biocoal, but when you talk about liquid and gaseous, you need Fischer-Tropsch, you need downstream refining. And what that means is you need multiple technology providers at the same site. I'm sure for all the engineers in the crowd, we understand that means exponentially more risk in getting all of this to work together properly. And the way we sometimes get around these is by using a good chunk of our incoming feedstock to provide the process heat and energy to process the rest of it. That means higher waste ratios and lower effective yields. Again, economics 101, if you've got low yields, you can't chase commodity products and hope to be long-term economically sustainable. So a little bit of science. What I want to focus on this slide is basically the lignin is the challenge we've always had to overcome. It's this amazing molecule that's been developed by nature, three-dimensionally cross-linked, resists chemical and biological degradation. It's why we use wood as building materials, and it lasts for hundreds of years. It protects the sugars in biomass, the cellulose and the hemicellulose, which are great molecules for structural stability, for carrying energy and all that stuff. But if you can't get through the lignin, it's really tough to do anything with it. And then obviously the inorganics depend on the species of what and how much they are. But what you can see here is we've actually figured out how to get the lignin out of the biomass at ambient conditions without damaging the sugars. And there's a massive industry dedicated to sugars, whether that's ethanol, whether that's follow-on glucose chemistry. We can do a lot with sugars with existing infrastructure, but if we alter them, then we're in a different pathway. So feedstocks, lots available in the world, billions, 100 billion plus tons a year. We don't use much of it now, and tragically, most of it, or a majority of it, is left to burn. It's burned intentionally through crop residue reduction or accidentally through wildfires. Significant release of carbon. It has massive long-term climate impacts, but if you've followed the news, Lahore in Pakistan and Delhi and Mumbai in India have just suffered through basically smog shutdowns. That comes from burning crop residue. It's small and medium farms. It's not some big faceless corporation, but in India, best data indicates about 100 million tons of crop residues burned every year. There's some value there. You return some carbon to the soil, but you have massive negative externalities. If we were to divert that amount of feedstock into our process and convert the cellulose to ethanol, so a low-value kind of end product, that's 1 million barrels a day of liquid fuels for a country the size of India, that spends a lot of its GDP importing liquid energy. So you can solve climate and health impacts, you can work with farmers for sustainable organic management, and you can take biomass-rich, energy-poor countries and change that calculus a little bit so they can invest in schools and roads and hospitals and all the things that raise the standard of living for the developing world. So this summarizes the process. I've talked about feedstock, talked about the process a little bit. Again, low carbon intensity because of ambient conditions. Our big reactor in Calgary is repurposed from the dairy industry, stainless steel jacketed tank, very, very simple. It's highly efficient. We recover and reuse our process chemistry. We only have one consumable in hydrogen peroxide. And on the right-hand side there, it's the optionality of products. So not just fuels, although that's a big part of the way forward, but sustainable chemicals and materials. And if you design the right-hand side of the process properly, the sustainable biofuels can be cost competitive with the fossil equivalent. Just to take away from this slide, lots of ways to take biomass and make other stuff out of it. Some biological, some chemical, some thermal, some are a mix. Typically though, those processes tell you what the products are going to be. So it's an oil, it's a gas, it's a solid. And sometimes those processes tell you what your feedstocks can and can't be. Species, ash content, moisture, and the like. What you should take away from this is that our process allows you to access all of those end markets, or fundamentally all of those markets. We don't make biochar, for example, but we do make a bio-crude that can go into upgrading, it can go into the chemistry side. But if ethanol's a strategic focus, cellulose can make ethanol, and most importantly, can make ethanol at any 1G ethanol facility in the world. They ferment, they hydrolyze starch into glucose, or they take sugar juice from beets and cane, and then they ferment it. Well, cellulose is just a polymer of glucose, arranged a little differently. Once it's hydrolyzed, which happens at lower temperature than starch, you've got glucose fermented at any 1G facility. It's now a 2G facility. So significant power to unlock existing infrastructure. And then I'm just going to use this as the kind of leaping off point. So as you can see, there's two of the circles on the left-hand side. I want to focus on the cellulose, which is around about 40% of most incoming biomass, depending. This is notionally 100 tons of bagasse. We did source from India from a project partner. And then the second one is the lightweight fraction of our bio-crude. So it's around 40% of the bio-crude, or about 10% of the incoming biomass. And if you look to the right-hand side, you can see the cellulose. The market I'm going to talk about today is using it in renewable natural gas or biomethane as a productivity enhancement tool. And then the lightweight fraction, we're going to talk about it in not necessarily refineries, but the terminal and tank side of refineries as a drop-in additive into diesel. So for RNG, we've done about 2 years of work. We've done an on-farm trial, and we've done 2 trials with the University of Alberta with the gracious and always welcome support of Alberta Innovates. What you can see on the left-hand side, why does the cellulose work? Well, because it's never seen heat, it retains very high surface area. Think of an egg. You crack it open, it's liquid, it goes wherever you want it. As soon as you cook it, the protein denatures, it turns into a solid or maybe a slightly runny solid, but you can't uncook the egg. Cellulose is very similar. Once you collapse that structure, it's kind of irretrievable. So we don't do that. The highest temperature the cellulose sees might be 40 degrees centigrade, so basically ambient conditions. Very low lignin content, under 0.5%. The lowest we've seen is a little under 0.1%. Lignin is an inhibitory compound, can be actually biocidal if it accumulates. We can also add other functionality because of the absorptive capacity of cellulose. So you could put buffers in there or H2S scavengers or whatever else the digester needs. But that cellulose is very highly bioavailable for bugs. That's why it works so well in fermentation as well as digestion. And a little bit goes a long way. So the right-hand side is the second trial. We had a 60-day stabilization period, had a control reactor and a test reactor, kind of 25 liters in volume, got to steady state, and we started dosing our test reactor with 2.3% cellulose. So we basically took out 10% of the feedstock, which was straw, from the control reactor, replaced it with 2.3% of our cellulose. So attempting to keep the cellulose content of each digester about the same and seeing what happened. And you probably can't quite see the numbers there, but the delta across the 90-day dosing period was an 85% increase in biomethane production. The interesting thing is it's not just more volume. It was about a 10% increase in methane concentration in the biogas and a 50% reduction in H2S from a little over 1,000 parts per million to just under 500 parts per million. So significant improvements there. Sounds great. I'm sure all the business people in the room, what does it cost? At this level of dosing, we can produce incremental biomethane at under $25 a gigajoule, but that's before you take into account potentially lower feedstock costs and definitely lower processing costs. So this could be something that at lower dosing where it's a little bit more effective, we could be quite cost competitive, maybe not with Alberta natural gas given some of that, but certainly retail pricing for natural gas in that $7, $8, $10 per gigajoule range, we can be cost competitive with that. For the digester owner, zero capex. Don't need to change anything unless you might need more processing capacity on the back end, but you can adjust your dosing to optimize that. And for designing digesters, we heard yesterday we only use about 15% of the feedstock that's available for RNG. A lot of that's because Canada is such a big country. There's dairy farms, there's feedlots that have maybe just about enough manure to produce enough methane, but not quite enough because of logistics, because of pipeline connectivity, because of distance to market, whatever that is. But if the same amount of manure could produce 30, 50, 80% more methane with our cellulose, now all of a sudden that capture area becomes really relevant. So stranded feedlots in northern Alberta or northern BC or remote parts of Ontario and Quebec now all of a sudden become viable candidates for RNG. So it's not just about today's assets, it's also about tomorrow's. And then the kind of newest and most exciting product, about 40%, the light fraction of our biocrude is immediately miscible in hydrocarbons and diesel. So we don't need to refine it. There's no cracking or hydrotreating or anything required. It was miscible at up to 5% in rack and raw diesel. And what you can see in the top right is we took Alberta summer diesel from the next door gas station. We added in 400 parts per million of our light fraction, and what we saw was the flash point got a little higher. That means it's a little more safe. The cloud point was within the error of measurement the same. So it says it got lower, but it's the same. In Canada, cloud point matters. Biodiesel consumers will tell you that. So no impact on cloud point, and we met the wear scar diameter, the lubricity test, at that 400 parts per million. But because we don't have low temperature issues, we don't have high temperature volatility issues, this will stay in solution basically through the entire operating temperature window of your fuel. And it has a CI in a worst case of about 30, in a best case at about 5. So yeah, 400 parts per million is a very small amount, but there's a non-negligible CI reduction that potentially could help us decarbonize diesel. But what's really interesting is the next step we're going to take. So because this is miscible at up to 5%, the next tests will be making sure we meet all the ASTM specs, commercial specs for rack diesel and rack marine fuels in various applications, and then progressing to engine testing. We've talked to some people here. We're really interested in continuing that discussion. OEMs, fuel associations, refiners, blenders, and end users. There's a way here to blend at, let's say, 5%. You could decarbonize your diesel by 3.5%, 4.5% with a 5% blend. And if we've done our homework, you don't affect the performance of the fuel, or more importantly, the life of the engine. So lots to think about here. We've talked to airports about decarbonizing ground equipment. We just heard how SAF is tricky to get into Canada. We're a big country with not a lot of infrastructure for it yet. But when we talk about airlines, air travel, marine fuel, we can decarbonize these things in small measures, but we can do it essentially with just our plant and blending at the tank side. So the refiners, we can take 5 years to figure out how to refine our heavy fraction. We've got commercial outlets for that today as a corrosion inhibitor. But if we can decarbonize diesel at 3%, 5%, whatever the number is, it starts to look a little bit like the success story we've had with ethanol and gasoline. And we can be a world leader in that, and we can ship this anywhere in the world as well. A quick word on what we're doing commercially. So we've brought this technology to the start line, let's call it. So we're TRL 8. We run a commercial scale tank in Calgary, 20 cubes, can process 3 to 5 tons a day of biomass as needed. As you can see, it's a dairy tank, slope bottom tank. We put some extra jacketing and measurement ports in it, but for all the fabricators in the room, it's very simple. Unfortunately, it's not going to be a very expensive piece of kit, but for technology developers, it's not going to be a very expensive piece of kit. We've done hundreds of reactions at multi-thousand liter scale, so we're very comfortable with the corrosion, with the reaction kinetics, with the mixing, all of those things we're very comfortable with. And then this is behind the kind of $30 million we've spent getting to this stage. And then the next step is we're in the market now to finance our first-of-kind facility. It's going to be the repurposing of an existing biodiesel facility. And one of the reasons that's the case is because the way we process our biocrude to get to a hydrophobic product is the biodiesel process, esterification and solvent recovery. So off-the-shelf existing processes, vendors, fabricators, installers, operators, it's all the same. We just put in a different feedstock, end up with our biocrude, and about 80% of the equipment basically on any biodiesel site can be repurposed to our technology. Front-end tanks, a little bit of extra distillation, and you're ready to go. This will be a 25 ton per day facility with potential to expand. It take us about 12 to 15 months from financing close to be up and running. The big unknown is the provincial permitting process, but Ron, our VP of Business Development, knows where all the skeletons are in the Alberta provincial closet, so we'll hopefully bring those to bear. And what we look forward to is touring anybody who's interested, in this room or not, around the facility, showing what it can do, sharing samples, doing extensive testing, whether that's engines for fuels or refining or biochemicals. We can convert our cellulose to CMF and levulinic acid at very high yields. So it's really unlocking what this pathway looks like, so that the ultimate users of this technology, the licensees and the end users, get the maximum benefit. I suppose the last thing I should say is not only do we have a great return out of this, but part of it is due to 5 million Canadian that we got from Emissions Reduction Alberta. Went through the full kind of dog and pony show in the grant process there and came out successfully on the other side. That QR code will set up an email to our team. If you want to learn more, hit that and hit send, and we're happy to engage, chat kind of technically, commercially, whether you're interested in potential partnerships as a product producer or a licensee or an investor. We're happy to chat with anybody, and obviously if you're ever in Calgary, we do a great job of hosting people. So thank you very much.